Okay, so in this video and in the next couple of videos, I'll discuss simple linear regression and multiple linear regression. And this will get, I'll derive everything. I'll derive all the maths that you need, using all the maths that you need, the parameters and stuff. So yeah, if this does require some basics of probability and statistics. So if you don't know that, just watch my playlist on probability and statistics. If you understand everything there, you will understand everything here as well. So, simple linear regression is actually a very old technique. It's it was first coined in 1886. The term regression was coined in 1886. So, what simple linear regression tries to do is, so first off, simple linear regression only tells, uh, it only gives one relationship. Okay, so if you have one response variable and one explanatory variable, then you can use simple linear regression. Suppose I have some independent variable x. My data set has only two variables, uh, x and y. Okay, x is independent, y is dependent. And if I want to find the associative relationship between these two, I use linear regression. Now, linear regression, as the name suggests, it's a regression technique. So you cannot use. So basically, this works as if you have your response variable in a real value, right? It can be positive, negative, anything. So my dependent variable is y, and my independent variable is x. So when I use linear regression, what I'm essentially trying to do is I'm trying to find the best fit line that passes through these data points. Okay, these dots here are data points, and I'm trying to find the best fit line. We all know that the equation of line is y equals mx plus c, right? So using linear regression, I want to establish or approximate these parameters m and c, okay? M comma c are parameters in linear regression, and we need to estimate them, okay? So that's what I try to do using simple linear regression. So simple linear regression helps find the existence of an association relationship between the dependent and the independent variable. Simple linear regression implies that there is only one independent variable in the model, okay, which is x. You don't have multiple features, you have only one feature, x. It could be anything. I'll give you just an example. X can be the height, okay, and y can be the weight. And we can generally be seeing that as the height increases, the weight also increases, right? Generally, that's what's observed. So using linear regression, we can find a relationship between these two variables. And yeah, both of these are real values, right? This is not classification where you have two classes, 0 or 1. That's incorrect. You have real values over here. So now another thing to understand is that linear regression does not help establish causal relationships, okay? If you want to see if there's a causal relationship in your data set, then you would have to use something like the Rubin causal model. Okay, there's this model called Rubin causal model, which helps find if there's a causal relationship in your data set. But linear regression does not help, uh, establish if there is a causal relationship in your model. That's incorrect. I won't be covering the Rubin causal model here. I'll just start with linear regression right away. So, linear regression is basically trying to find a relationship between the independent variable x and the variable y. I'll write the relationship as beta naught plus beta 1 x. Okay. Y is your independent variable. X is your dependent variable. Sorry, y is your dependent variable and x is your independent variable. Okay. And I'm trying to find some parameters beta naught and beta 1 such that beta naught plus beta 1 x gives me a value equal to such that beta naught plus beta 1 x gives me a value of y, which I'll call y hat, which is the y predicted value, plus some error term. Okay. So what is this error term? The error term is basically y minus y hat, which is equal to y minus beta naught plus beta 1 x, because chances are that our linear regression model will not be able to establish a perfect relationship with our dependent variable, right? So that will lead to some errors. Okay. So between the predicted value and the actual value, and that error is given by y minus beta naught plus beta 1 x. This error is also called the residual. Okay. It's also called the residual. So now that we know what the regression parameters are, which is beta naught and beta 1, these are the parameters, the regression parameters. So the entire point of linear regression is trying to find the best fit for these parameters and trying to estimate them. Okay. Beta naught plus beta 1 x is the conditional expected value of yi, for which we have given the value of xi. Okay. That's what I just wrote here. Now, the linearity condition of linear regression, before I start the derivation, I just want to say that the linearity condition of linear regression is defined using values of beta naught and beta 1, not xi. Okay, that's important. What does that mean? It means that if I have y equals beta naught plus beta 1 x square, or if I have y equals beta naught plus beta 1 log of natural log of x. Okay, this is also perfectly linear because the linearity condition of linear regression is defined using values of beta naught and beta 1. Okay, not x. However, this would be nonlinear regression if nonlinear regression would be something like y equals beta naught plus ln beta 1 x, or y equals beta naught plus e to the power beta 1 x. Okay, this is a nonlinear regression uh, relationship between the independent variable and the response variable. So nonlinear relationships can be uh, connected to linear relationships by applying some suitable transformation. So if you want to convert this to a linear relationship, you would have to apply some transformation to get this to the form of beta naught and beta 1. If you do that, you can convert it to a linear regression relationship. Okay. So now we optimize the linear regression using the ordinary least squares method. So what is the ordinary least squares? I told you that errors are given by y minus y hat, which is equal to y minus beta naught minus beta 1 x, right? So ordinary least squares is, I'll write it here. Ordinary least squares is given by sigma I equals 1 to n y minus y hat the whole square. Okay, I basically want to minimize the errors. This is the error, right? This is nothing but the error squared. So I want to minimize this value as much as possible, because the thing is, the idea is that if I can minimize the errors, I can get a value for my parameters beta naught and beta 1 ask such that it very very closely resembles the actual response variable y, right? um, so if the error is 0, that means that y hat is exactly equal to y. My predicted response variable is exactly equal to y, and that's good. That's exactly what we want. So we basically want to minimize the errors. This is our optimization problem. Okay, right. So how do we go about minimizing this? So, well, we estimate the parameters using minimizing the ordinary least squares. This is called ordinary least squares, right? So now before we start, uh, there are some assumptions that linear regression makes. I'll write them down here. Just stick with me for this, and we'll come back to these assumptions when we are actually deriving everything. Okay, so first off is that the linear regression relationship exists between y, beta naught, and beta 1. Okay, you're trying to establish a relationship between beta naught and between y, and by finding the parameters beta naught and beta 1. The second one is that x, that is your independent variable, x is non-stochastic. Okay, which means that it's deterministic. This is a very important assumption that we have to make in order to arrive at the parameter value for beta naught and beta 1. The third one is that the expectation of the error I given some value xi is equal to 0. Okay, what this basically says that if I have, I just want to geometrically explain what this means. Is that it, what it means is that if I have points, okay, like this, these are my points, right? The independent points x, and this is the line that I formed, okay, the best fit line that I got. What this means is that, look, this distance between this point and the line will be e1, error 1. This distance between this point and this line will be error 2. This will be error 3. This will be error 4, and so on. What it means is that if I add all of these errors and I sum them up, I should get 0. Okay? That is what it means. So the expectation of all the errors given xi is equal to 0. That means if I sum up all these errors and I add them up, I will get the value as 0. Okay? Because error 1 will be positive, error 2 will be negative, etc. What this also says is that there exists a relationship where I can get a value of y hat such that it's exactly equal to y. Okay, I can find the best fit value of this line and the parameters. That's what it says in non-mathematical terms. Okay, basically just says that the best fit line exists. A best fit line exists, right? The fourth one is that the covariance between two different errors, eta I and eta j, okay, the covariance between two different errors is equal to 0. This means that the errors are not correlated. Errors are not correlated. Okay, this is the fourth assumption. The fifth assumption is that the residuals, which is the errors, right? EIs, they follow a normal distribution. Okay, my errors follow a normal distribution. This is the fifth assumption that I make when I have to derive my linear regression parameters. And the sixth assumption, the final one, is that the variance of eta I given some value xi is constant. Okay, I'll come back to this later. This condition is also called as homoscedasticity. Homoscedasticity. Okay, the variance of all my errors given some value of xi is constant. That means all the errors have constant variance. They are limited by a range. They don't spread out. So if my errors are limited in this range, it's called homoscedastic. If I have errors that spread out like that, it's called heteroscedasticity. In which case I cannot model my data using a linear regression model. Okay. So now that we know all of these assumptions, let's actually go on to deriving the parameters. How do you derive the parameters beta naught and beta 1? Okay, so let me just change the page. I'll start on a fresh page. The derivation will get a little long, but It's okay. It's not very hard. So let's assume that I have points y1, x1, comma y2, x2, all the way to yn, comma xn, right? This is my data set with n observations. Now, using the assumption of 3, the third assumption that I said, the conditional expectation is 0 of the residuals, I can say that expectation yi given xi is equal to expectation beta naught plus beta 1 x plus eta. Okay, this is equal to, using the properties of expectation, I can expand this as expectation beta naught plus expectation beta 1 x plus expectation of eta, which is the errors. Now, from my third condition, which says that the expected value of all the errors is 0, this goes to 0, right? So I'm basically left with just beta naught plus beta 1 x. Because now, why am I allowed to do this? Because beta naught and beta 1 are just parameters. They have just one single value. So there's no point saying expectation of one single value. The expectation of a single value is just the value itself. And why am I allowed to do it for x? Because x is deterministic. It's not stochastic. Okay. Yeah. So the parameters x values is non-stochastic, and this is 0. This is the assumption that we make when we try to find the value of linear regression, right? So now that we have this, the sum of square errors, okay, which is sum of square errors, is given by sigma ei square, where I equals 1 to n. Okay, this will be written as sigma I equals 1 to n yi minus beta naught minus beta 1 x the whole square, xi the whole square. Okay, so this is my sum of square errors. Now, to find the optimal values of beta naught and beta 1 that will minimize the sum of square errors, I have to equate the partial derivative of the sum of square errors with respect to beta naught and beta 1 to 0. Okay, which basically means I have to find dou SSE by dou beta naught equal to 0 and equate it to 0. And also I have to find dou SSE upon dou beta 1 and equate it to 0. Okay, this will give me the best fit values of my parameters beta 1 and beta 1x such that the line fits the dataset perfectly. Okay, so let's start with the derivation. So first up, if I take dou SSE upon dou beta naught, I get sigma I equals 1 to n minus 2 yi minus beta naught minus beta 1 xi. Okay, this is equal to 2 into n beta naught plus beta 1 summation I equals 1 to n xi minus summation I equals 1 to n yi equal to 0. Okay, this I've just bought the summation n and I've calculated it multiple times. Okay, I've just expanded this equation into this. That's all I've done. So now we equate this to 0. Okay, we equate this to 0. When we do that, 2 goes down, that becomes 0. We need to find the value of beta naught. I'm trying to find the value of beta naught over here. Okay, so beta naught is equal to summation yi equals 1 to n minus beta 1 xi summation I equals 1 to n. Okay, and if I bring this n down here under in the denominator, then this basically becomes the mean, right? Similarly, even this becomes the mean. This and this it becomes the mean. So I can write my value of beta naught as y. This is beta naught predicted. Okay, everywhere it's beta naught predicted, right? So I can write beta naught as y mean, the value of y, the mean value of y minus beta 1 predicted x mean. Okay, so this is my value for beta naught. Let me just, so all of these main equations and formulas, right? I'll color them, I'll make a different colored box around them. Just write this down. This will come in handy when we are trying to find the value of beta 1. So this is beta naught. This is how you estimate the value of beta naught. Now similarly, you need to estimate the value of beta 1. So it's tau SSE by tau beta 1, which is equal to summation I equals 1 to n minus 2xi yi minus beta naught minus beta 1 xi. Okay, this is equal to minus 2 summation I equals 1 to n. Watch this carefully. Xi yi minus beta naught xi minus beta 1 xi the whole square, xi square, not the whole square, equal to 0. Okay. My handwriting is a little bad on this. The notepad is very slippery, but I'm hope you can understand this. It's beta 1. Right. What I've done is I've just brought the x inside and multiplied everything. That's all I've done. So over here in this beta naught, I'm going to substitute this value. Okay. I'm going to substitute the value of beta naught from here. Right. And I'm going to expand this and write it as, I'm also calculating this in my head, so it's a little slow. So I'm going to write this as minus 2. I'll bring the 2 outside. Summation I equals 1 to n xi yi minus xi y bar plus beta 1 xi x bar minus beta 1 xi the whole square. Okay, I've just substituted the value of beta 1 with this. I've expanded it. That's all I've done. There's nothing different. It's very simple. And okay, so I'm going to do some moving around. I'm going to move things around a bit. And I'll write this as I equals 1 to n xi yi minus xi y bar, okay, minus beta 1 summation I equals 1 to n xi square minus xi x bar. Okay, this is equal to 0. I've just taken this in one. Sorry. Yeah, so all I've done is I've just grouped this and this and this and this, and I've expanded. I've just opened it up a little. Okay, so now I have this equation. From here, I'm going to take the value of beta 1. Okay, I'll just bring this to this side of 0 and I'll find the value of beta 1. So beta 1 is basically summation I equals 1 to n xi yi minus xi y bar whole upon summation I equals 1 to n xi square minus xi x bar. Okay, this is the value of beta 1. Now this is a little, is there any way to make this shorter is my question. Well, there is. You can make it a little shorter. You can just bring xi out. So this is I equals 1 to n, which is xi yi minus y bar upon summation I equals 1 to n, you have xi and xi minus x bar. Okay, right? So we have this. So just remember this or write this down. I'll switch to the next page. So now that we have that, now we're going to manipulate that equation, and we're going to manipulate a little. So now I know that summation I equals 1 to n x bar y bar minus yi x bar is equal to 0, right? This is a property of mean. I take x bar outside, and y bar minus yi summed all the points summed together will be equal to 0. This is a property of mean. This I've covered this in my very first videos in probability and statistics. And similarly, I also know that summation I equals 1 to n x bar the whole square minus xi x bar is equal to 0. Again, property of mean. Okay. So these are the two equations that I know from properties of mean. And I can write this previous equation that I wrote here. I can write this equation as the follows. Okay. Beta 1 hat is equal to summation I equals 1 to n xiyi minus xiy bar plus summation I equals 1 to n x bar y bar minus yi x bar, okay, whole upon summation I equals 1 to n xi square minus xi x bar plus summation I equals 1 to n x bar square minus xi x bar. Right? Look, this is equal to 0. So adding it, I'm just manipulating my previous equation a little. Both these values are equal to 0, so I'm just adding it here. And then I have this. Okay. So now when you manipulate this a bit, you open things up and you move things around. It's easy to see that this equation becomes sigma I equals 1 to n xi minus x bar yi minus y bar whole upon sigma I equals 1 to n xi minus x bar the whole square. Okay. If you multiply whatever I have here in the brackets with one another, you will basically get back this same equation over here. Okay, I've just condensed it a little. So now this might look familiar to you. This is basically covariance of x comma y whole upon variance of x, where x is our independent variable. So that is the value of beta 1. The predicted value, if you want to estimate the best parameter of beta 1, it's basically covariance of x comma y and variance of x. Okay. So yeah, you have beta 1. And if when you have beta 1, you can just put it in the equation and find beta naught. Beta naught is equal to y minus beta 1 x, right? That's what we found earlier. Beta 1 predicted x bar, y bar minus beta 1 predicted x bar. X bar and y bar are the mean values. So this is how you find beta naught and beta 1. It's very simple. Okay. So this was the entire derivation of finding the best parameter values so that the line fits, so that we can find the best fit line for our data set to predict the regressor. So I'll stop the video here and I'll see you in the next video.